Hi everyone. In this video, we're going to continue on and actually finish chapter 4 by talking about a little bit more about the exponential distribution, and we're going to talk a little bit about the gamma distribution, which is um, the a sort of generalization of the exponential. So, exponential distribution is used in a couple of different situations, especially in engineering, in the different types of engineering that you are interested in. Okay, it's often used to model the distribution of time between occurrences of successive events. Okay, this is very similar to the Poisson distribution that we saw from chapter 3. And the book goes into a, a bit of a lengthier discussion about that than I'm going to do here. And so, if you want to read that, then I suggest you do because it's very interesting. Um, but it's connected to the Poisson distribution, um, and it's also often used uh, to model the distribution of component lifetimes. And so, components of a car or something else, components of a machine. You're often interested in how long that machine, how long is that component going to last you until you need to replace it again. Um, and we can use the exponential distribution to do so. And part of the popularity in measuring the component lifetimes is due to an important property that we need to discuss. And that property is called the memoryless property. Okay, the memoryless property, or some people call it the forgetfulness property. And what the memoryless property says is that a given probability distribution is independent of its previous history. Okay, now that probably doesn't make it any easier to think about what that means in this case. And so here's an example. If I install if I install a component part to something, okay, and I leave for some time, the book will call it T sub naught, but we don't need to worry about sort of mathematical formulas here. When I come back, the part is still working. So, in a sense, you buy a new car and you drive that car for 3 years, okay, and you're interested in how long before, I don't know, a spark plug goes on your car. Okay? The memoryless property says that the probability that that component lasts an additional t hours is the same as sort of before you left. So the probability that that part is going to fail, that spark plug is going to fail on your car, is the same after 2 years as it was the day you bought it. Okay, so that's the memoryless property. Now, that may be a reasonable assumption, or it may not, depending on the type of situation. And so certainly if there's wear and tear on something, or it's about you but you get tired, like shooting free throws or something, then you need to take that into account, and maybe the exponential distribution is not as sort of good for that, but it does exhibit this memoryless property, which can be advantageous. And so that's the important things about an exponential distribution that I think you should know about. And then we're going to move on to the last distribution that we'll talk about in this chapter, which is called the gamma distribution. Excuse me, so I had to take a drink. The gamma distribution, as I've said before, is the generalization of the exponential distribution. Okay, and it looks like this. So a gamma distribution has a PDF that looks like this. It has two parameters, alpha and beta. Okay, and so the PDF is 1 over beta to the alpha, and then it has this gamma function here. So this is a capital gamma of alpha. We don't really need to worry about the gamma function. It's another function that you have to do some integrating to. Rather, it's a harder calculation. We don't really need to worry about it because Minitab is going to do it for us. Okay, x to the alpha minus 1 times e to the negative x over beta. Now, x, again, has to be non-negative. It has to be positive. And it has two parameters, alpha and beta. They both have to be positive. Okay, x has to be non-negative. The parameters need to be positive. And we don't really need to worry about what they represent, in a sense, in this distribution. So for the normal, we had the mean and the standard deviation. Here we have alpha and beta, which are sort of like shape and scale parameters, but in a sense not. And so we're not going to worry about them at the moment. Now, it's important to note that they have there are different types of gamma distributions. This they call a standard gamma distribution, one that has beta being equal to 1. Okay. And it says given by 4.7, but of course we don't know what 4.7 is, so we just get rid of that last part. Don't worry about it. Okay. But that's the PDF. Certainly you can get the CDF and so on and so forth, but we aren't really interested in that. To get the mean and the standard deviation, the mean and the variance of the gamma distribution, you can look in the book, and I will show it to you later, but I don't have it on this slide currently. But again, for our last sort of slide in this chapter, let's do a example with a gamma distribution. So here another article, probability distribution of maintenance cost of a system affected by the gamma process of degradation. Notes that a gamma distribution is widely used to model the extent of degradation, such as corrosion, creep, or wear. Okay. Let X represent the amount of degradation of a certain type, and suppose it has a standard gamma distribution. A standard gamma means that beta, that second parameter, is equal to 1, and alpha is equal to 2 here in this case. I want you to find the probability that the degradation is between 3 and 5, and then at least 4. So, again, what are we going to do? We're going to turn to Minitab. I want to calculate some probabilities, cumulative ones, and I'm interested in the gamma distribution. So again, shape and scale it has here. Shape is alpha, scale is beta. It's important to write down. Shape is alpha, 2, scale is beta, 1. Okay. Don't worry about this threshold parameter. It's always going to be 0 for us. Okay, and specifically, I'm interested in, if we go back here, 3 and 5. So, actually, let me say here 5 and 3. Okay, 5 and 3, and then let's go back and do that calculation. Cumulative probability, gamma, shape 2, scale 1. The values are in C1, and so we click OK. Okay, gamma with shape 2 and scale 1. 5 is 0.959, and 3 is 0.800, so 80801. And so when you subtract those two, you're going to get the answer. So you could do that if you wanted to. I won't do it right now, but those are the two. You just subtract them to get the final answer. And then the last one is at least 4. So at least 4 is 1 minus at most 4. And so I need to do 1 minus the CDF of the gamma distribution at 4. So again, I go to calculate. probability distribution is cumulative. Now I want a single value. The value is 4. Click OK. And now we get the answer, which is, well, not quite the answer, but almost the answer, 0.908. And of course, to get at least 4, we need to do 1 minus this. And so that would be 1 minus 0.908, which would be 0.012. Okay, 0.092. And so that would be the final answer for that last part. And that is the end of chapter 4. Certainly there will be problems, exponential and gamma. I didn't give you any your turns because I think it's pretty self-explanatory now how to use Minitab and get those kind of answers. So I'll see you next time.